Hello everybody and welcome to the first class of ATMO 412. Today we will begin by introducing some of the basic concepts that we'll need for the remainder of the course, and these will be concepts that will be important to deal with some of the more complex topics that we'll introduce next time and in the following lectures. In particular, today we're going to review the basic equations of motion in the atmosphere. We're going to review important concepts such as the thermal wind. We're going to talk about geopotential and geopotential heights, and we're going to talk about vorticity, which is also sort of a good friend of anyone who studies fluid dynamics on a rotating sphere. Okay, so this class will be mostly concerned with synoptic meteorology, and so why don't we start with answering the question of what is synoptic meteorology? So when we talk about synoptic usually refers to a particular scale, both in terms of spatial scale, and a temporal scale. And when we think about synoptic meteorology, synoptic weather, we talk about what we intend as weather. Okay, so weather systems such as extratropical cyclones, high pressure systems in the subtropics, or low pressure systems, the motion of the jet stream. We'll talk about waves in the atmosphere, so troughs and ridges, and we'll talk about fronts. And synoptic is typically a scale of something like 1,000 kilometers, okay? 1,000 to 6,000 kilometers. And in terms of temporal scale, we're thinking anywhere between 1 day and 1 week, let's say. Anything greater than 6,000 kilometers and greater than 1 week, we typically refer to as planetary scale. And so trade winds, for example, are an example of planetary scale motion. And lower than 1,000 kilometers and lower than 1 day, well, that depends. If we're thinking between 1 kilometer and 1,000 and between 1 hour and 1 day, then this is mesoscale meteorology. And examples of objects that concern mesoscale meteorology are thunderstorms, or things like land sea breezes, or mesoscale convective systems. Well, they have the word mesoscale in them. And below 1 kilometer and below 1 hour, we're talking about microscale stuff. So turbulence, planetary boundary layer dynamics, the puffy cumulus clouds that we see here in Hawaii, they're all example of that. So we are obviously larger than mesoscale and below planetary scale, but you need to keep in mind that these scales are completely artificial, right? We came up with them based on observations, but there isn't really a hard cutoff. And so when we get closer to 1,000 kilometers, then it's really a judgment call whether we're thinking about mesoscale or synoptic scale, okay? And these scales, which is also what complicates the study of meteorology, the mesoscale, the microscale, the synoptic scale, the planetary scale, all these different scales interact strongly with each other. So there's no way to separate the scales, okay? And this is what makes meteorology particularly beautiful, but also particularly hard, okay? And when we think about synoptic meteorology, the star of the game are the quasi-geostrophic equations. We're not going to talk about quasi-geostrophic equations, but we'll introduce them in the next lecture. And the discovery of quasi-geostrophic equations, or if you will, the quasi-geostrophic approximation, was really a game changer in the history of numerical weather prediction, or in the history of weather prediction. I shouldn't say numerical necessarily, but in the history of weather predictions. So this is a summary. On this slide, I put a summary of the scales. As we said, we're between 1,000 and 6,000 kilometers. And so when you open weather charts, when you look at satellite pictures, for example, or satellite images, the features that stand out, typically, these are synoptic features, okay? One thing that is useful, and one of the reasons why I introduced this sort of scale I'm introducing these scales is that thinking about scales can be really important in the study of meteorology. Keep in mind that meteorology isn't necessarily like studying mathematics or studying theoretical physics. Meteorology is a very applied science, and this means that the equations of motion of the systems can be extraordinarily complicated, not only to study but also to use, and so to put on a calculator or also to interpret mathematically. And so scale analysis can help us in reducing some of these equations, okay? So getting rid of some terms that could be potentially relevant in the phase space of all possible configurations, but which on Earth don't really play a big role, okay? So thinking about scales is going to be useful, not only for now, but in general in this course and in the rest of your career. So always keep in mind all the different scales, okay? And we'll see examples in a few minutes when we start looking at we'll start looking at equations of motion, and we'll start to simplify some of these terms. Okay, so just as a recap, we are on a planet that is almost like a sphere. It's more like an oblate spheroid, but could be approximated to a sphere, and it's rotating. And this introduces a lot of complicated factors. In particular, this is what physicists call a non-inertial reference frame. And so we have things like the Coriolis acceleration or the Coriolis force, which is not a real force, but is due to the non-inertial nature of the frame of reference. And these complicate things substantially. And they make the equations of motion a little bit more complicated than they should be, or than they could be if we were not on a rotating planet. We will be mainly using Cartesian reference frames, and so X, Y, and Z normally, but sometimes we'll also be using other kinds of coordinate systems. And so, for example, instead of using vertical coordinate Z, height, altitude, sometimes we'll be using pressure. And even though we are more familiar with the concept of height, so measuring height in centimeters, using pressure sometimes can be useful and can make sense because unlike all of us, air is compressible actually. And so 1 meter, a thickness of 1 meter near the surface is not the same as the thickness of 1 meter at the top of the atmosphere. And sometimes we may be tempted also to use rotating coordinates. I don't know that we'll actually be using those, but sometimes they could be useful. Okay, so let's start with the governing equations. The atmosphere is by and large a gas, okay? And therefore it obeys the ideal gas law. I'm pretty sure you saw this in high school and many other classes that you took before. But just as a recap, this is a simple linear relationship that ties together some of the basic variables, some of the basic state variables of your gas. And in particular, this says that the pressure of a gas equals the density times a particular constant times temperature. Now notice that here I put subscript V. That's because this T here is called virtual temperature. And if we wanted to use the normal temperature only applies to an atmosphere that is made entirely of dry air. But we do know that the Earth's atmosphere also contains a gas known as water vapor. Many other gases, of course, but water vapor is pretty abundant and has a dynamical impact. And so if we want to use normal temperature, then we need to modify the gas constant. Otherwise, we can use the gas constant of dry air, and we can use what we call the virtual temperature. And virtual temperature, I wrote down here how it can be computed. It's simply a linear combination of the temperature and the water vapor mixing ratio. Hopefully this doesn't come as a news to any of you, okay? The gas constant for dry air, you should know this. If people woke you up in the middle of the night and asked you, what is the gas constant for dry air? You should know on top of your head that the gas constant is approximately 287 joules per kilogram per Kelvin. I hope that this number you'll remember, and if not, please do, because it comes, it's this and the specific heat at constant pressure. These are constant that come time and again in the study of the atmosphere. Okay, so, keep in mind, ideal gas law, considering the virtual effects due to the presence of water vapor. In terms of the motion of the gas is obviously not in a box, but is free to move. And we describe the motion of the gas using momentum equations. And these momentum equations, if we can focus on horizontal momentum equations, these are written by these two equations over here. And it can be shown that the change, in particular, careful here, I'm showing the total derivative of U and V. This component of the wind is sometimes known as zonal wind. This is known as meridional wind. The total derivative of the zonal wind equals the pressure gradient, or a term that is proportional to a pressure gradient, plus a Coriolis term, plus a friction term. And something similar applies to the meridional component. Notice that these two equations are coupled, meaning that the equation for the zonal momentum includes meridional momentum and vice versa. This is the equation for the meridional momentum, and it includes the zonal momentum. So they cannot be taken apart and solved separately. They have to be solved at the same time. These two terms constitute what we call frictional terms. And this is the zonal and this is the meridional component of the frictional terms. These are typically, they exist and they're the strongest in the boundary layer, where the flow feels the effect of the surface. Okay, the boundary layer is the bottom of the atmosphere where we have the overturning circulation. These are the terms that impact the momentum in the boundary layer. Typically in the free troposphere, these can be ignored, and typically we will be ignoring them, okay? We can also rewrite these two equations in a simpler form. You don't need to, but if you want to save some ink, you can rewrite them like this. It's exactly the same form. We're not adding or subtracting any information. Be careful that when you write it like this, you have to specify that this is just the horizontal gradient. So it's either ddx or ddy. And this is a simple cross product that if you work out all the terms, it gives you exactly the terms that you need in order to get these two equations. And finally, the total derivative. Remember that when you write down the total derivative, this includes not only the temporal derivative, but it also includes the advection terms. Okay, and these can be rewritten as a cross product of the wind vector. And now this is the three-dimensional gradient, okay, not just the two-dimensional like this with the subscript h, okay. So in this case, the momentum equation is telling us that the rate of change of zonal or meridional wind is due to advection, horizontal and vertical. It's due to pressure gradients, and it's due to Coriolis torque or Coriolis force, and also the zonal component of the frictional force. Okay. All right. So these equations are pretty complicated because they contain a lot of terms. And so can we use some simple scale analysis to get rid of some of these terms? We can certainly go and check the scales. Here on the left, I put the symbol that indicates what kind of scale we're thinking about. These are the magnitudes, and this is a description. And we will examine now the different equations, and we will substitute these terms to the equations. Notice when we look at the scales, Notice the disparity. Notice that the this U is the horizontal velocity scale. So it's good for zonal or meridional winds. Here we're talking about 10 meters per second. And here we're really thinking about orders of magnitude, right? So it doesn't matter if it's 30 or 32 or 8. Order of magnitude is 10 meters per second. Notice that this is a lot higher than vertical velocities. Now, if you've ever looked into a cloud, clouds can have vertical velocities that are a lot higher than that. And so how do we reconcile this thing? Well, we reconcile it by remembering that we're only thinking about the velocity scale at the synoptic scale. So while individual clouds might have really high vertical velocities, either ascending or descending, the vertical velocity on average on scales of 1,000 kilometers is usually pretty low. It's usually of the order of a few centimeters per second. Okay, this is the velocity, for example, of the subsidence that is on top of our head over the boundary layer in Hawaii. Okay, the depth of the boundary layer is about 1 kilometer, give or take. Again, sometimes it's 500 meters, sometimes it's 2 kilometers, but it doesn't matter. The vertical pressure change over the troposphere is about 1,000 hectopascals, or 10 to the 5th pascals. Horizontal length scales, we said about 1,000 kilometers, so 1 million meters, and so forth. Okay, we can substitute all these different terms. Well, if you do, if you substitute them into the pressure, the momentum equation that I showed you before, you'd find that the advective term over here, excuse me, and the frictional terms over here are really, really small, and they are an order of magnitude smaller than these other two terms. And so this teaches us an important lesson that in the atmosphere, typically, there is a good balance between the pressure gradient and the Coriolis force. Okay, is this balance always? Is this balance exact? Of course not. And there are times, there are occasions in which this balance is grossly not respected, let's say. But in general, it's a pretty good approximation. And this balance between the two, if you rewrite down the equations, you can apply another cross product so that you can get the velocity, the wind velocity free, and you get the cross product with the gradient of the pressure field. This wind that results from this condition is known as the geostrophic wind. And it's a pretty good approximation to assume that the wind is in geostrophic balance. This is also what we say sometimes, is in geostrophic balance. If you want to be even more exact, that you can relax some conditions and you obtain what we call the quasi-geostrophic approximation, which is what we'll talk about next time. But by and large, geostrophic wind, not a bad assumption. So the vertical momentum equation is slightly different on the other hand, and it also includes the gravitational force, and you can show that the equation for the vertical momentum is this one. So again, we have a total derivative, we have a pressure gradient, we have something that depends on the Coriolis parameter, something that depends on gravity, and something that depends on frictional terms. Plug in the terms that I showed you before from the scale analysis, and you obtain that actually this term over here, the pressure gradient, and this term over here, the gravitational acceleration, they're pretty much in balance. Okay, so you can multiply everything by rho, and you have that dpdz, the vertical gradient of the pressure field, is approximately equal to the gravitational acceleration and the density. Okay, this is known as the hydrostatic approximation, or hydrostatic equation, if you will. And it's a pretty good approximation to assume that the atmosphere is by and large in hydrostatic approximation. This is not true if you go to really small scales. And so if you consider a supercell storm, for example, a supercell storm is absolutely not in hydrostatic approximation. But if you consider trough in the atmosphere, the synoptic scale, then this approximation is pretty good. Also, what we're saying here is that this term is negligible, right? This means that dw dt is 0. And so this might give you the false impression that there is no vertical motion at all in the atmosphere. This isn't actually true, right? There can still be vertical motions, and we'll see how in a moment, and we'll talk about vertical motions a little bit more next time. We get to talk about vertical motions here because the other equation that is important when considering the motion of the atmosphere is the continuity equation, right? The air is compressible, obviously, but air cannot be created nor destroyed, right? And you can sit down and write the equations very carefully, and if you write the continuity equation in differential form very carefully, you get to something that looks like this, okay? Notice that here we have two terms. We have omega and we have p. So normally you'd expect for a fluid of constant density, you'd expect dw dz. And so why do we have d omega dp? What the hell is omega and why is there a p? Well, there's two things. First of all, omega is the so-called pressure velocity. So it is not dz dt, which is the definition of w, but it's dp dt. So it's how much pressure changes over time, okay? And this velocity, if we consider the isostatic approximation, is obviously related to the normal velocity, to what we would call velocity. And the reason why we like it and the reason why we have pressure here, and we like pressure so much as a vertical coordinate, is that, as I said, the air is compressible, right? And so 1 meter near the surface is not exactly like a meter at the top of the atmosphere. And so in many ways, the case could be made that pressure is a much more reasonable coordinate to use when dealing with the atmosphere. Now, strictly speaking, the mass of the atmosphere is not conserved, right? We do know that there is constant evaporation from the surface, particularly the surface of the ocean. Excuse the random noise that comes from airplanes and ambulances and whatever. Also, so the water vapor, whatever is evapotranspired from the surface contributes to an increase of the mass, but also there's rain, and rain reduces the mass of the atmosphere, okay? So if we want to be really, really precise, then here we'd have to include an E minus P, where E and P are respectively the evaporative fluxes and the precipitation rates. Okay, we're not going to do this, but it's a pretty decent approximation to use this, but if you really want to be perfectly exact, then you have to include these terms too. Okay, so very good. So we have momentum equation, continuity. What next? Well, the gas also exchanges energy with its surrounding, and if you remember your thermodynamic classes, then you remember the first law of thermodynamics, and your teacher, whoever taught you that law, might have stressed at some point that the first law of thermodynamics is really a statement about conservation of energy, and this is really what it is, okay? The way that I expressed it here is to say in differential form that any exchange of heat must equal the sum of the changes in internal energy, and this, which is essentially what you'd consider as work in thermodynamics, in this case is work done against the force of gravity, okay? And there are many processes. This is the other constant that I mentioned earlier. This is specific heat at constant pressure. This, together with the gas constant of dry air, this is another universal constant in atmospheric sciences. Its value is about, give or take, some per mil, is about 1,000. It's about 1,000, what's the unit of measurement? I believe it's 1,000 joules per kilogram per Kelvin, again, again, okay? And there's also the specific heat at constant volume, which is specific heat at constant pressure minus the gas constant, okay? So it's about 717 joules per kilogram per Kelvin. Hopefully none of these things are news to you, okay? So keep in mind these values. I don't think that you should memorize a lot of values in your life, but these you should try and memorize, okay? Okay, good. And this equation is actually important because it could be used for a variety of applications. So for example, imagine that there is some processes that are happening without any heat exchange. These processes we call adiabatic, and in this case, dq equals 0. And if that's true, then you can simplify these two terms and you can write dt dz, and this equals modulo sine equals to g over cp, which is about 9.8 Kelvin per kilometer. dt over dz is what we would call the adiabatic lapse rate. In particular, it's called the dry adiabatic lapse rate. It's a fairly good approximation in the atmosphere to indicate how quickly air cools when you lift it from the surface, only insofar as you ignore the presence of water vapor. This may be a good approximation, but at some point, especially in the free troposphere, you will have to take water vapor into account. And so this is a good first approximation, but in the atmosphere, you'll have to consider the moist adiabatic lapse rate that is closer to 6.5 Kelvin per kilometers. And you can also play a little bit around with this equation and use the hydrostatic approximation and the ideal gas law, and you'd get to the definition of a new temperature, and we call this the potential temperature. And this depends linearly on the temperature, but it also contains this strange nonlinear term that is inversely proportional to atmospheric pressure elevated to some power that is about 0.286. That is the gas constant divided by the heat capacity at constant pressure, okay? Now, this temperature, called potential temperature, is the temperature that a parcel would have if you were to bring it adiabatically to the pressure P0 from any pressure P, okay? And this, because of how we defined it, this is conserved for adiabatic motions. And so this is a nice definition because it gives you a variable that doesn't change value if you move the parcel up or down, provided that there's no water vapor that complicates things, so there's no condensation, there's no evaporation. You're just moving this parcel up or down and laterally and what have you, then the temperature will vary because the parcel will expand and contract and there'll be adiabatic compression or expansion, but theta will remain the same. So compressions and expansions will happen, but this theta will remain the same. And this will give you a way to compare air parcels that exist at different altitudes, okay? So we like conserved variables. And so, for example, if we think about the bottom of the atmosphere, the bottom 1 kilometer of the atmosphere, this is what we call sometimes the boundary layer, the planetary boundary layer. The potential temperature in this planetary boundary layer tends to be fairly constant, okay? So this is a sketch of what theta might look like as a function of height. There's a little bit of decrease from the surface, and then it tends to be pretty constant over the boundary layer, and then there's typically an inversion layer, and then it keeps going, and it typically increases with height. Why is it constant here in the boundary layer? Well, the boundary layer contains all these eddies that are constantly stirring up the layer, and so on average, you have this mixing of this variable, and this variable in the boundary layer, typically there's no moist processes, so there's no condensation or evaporation typically, and so you have this variable that is conserved for bringing parcels up and down, and you have this situation where there's this constant mixing, so it only makes sense that this would be constant. Notice that the constant is only in statistical terms, and so if you have a large field and you take the average, then the average will look constant. But if you were to fly through a boundary layer, then you'd notice pretty large variations. Okay, these variations will vary in magnitude. So according to the height, another way of saying this is that the mean is constant, but there's also a non-negligible variance in the boundary layer. An example of these mixed layers, here we have two different soundings. The left one is from Greensboro, North Carolina in August 2007. The right one is Dallas, Fort Worth in Texas in April of the year 2000. Pretty different situations. The red line, obviously, well, I'm assuming you're familiar with these, but the red line here represents the sounding of the temperature. The blue line is the dew point temperature. This is a skew T log P diagram. The dashed green lines that are tilted this way are isotherms. Okay. These are dotted green lines. The dashed black lines are moist adiabats. My bad. Let me try again. Dotted green lines are dry adiabats, so 10 Kelvin per kilometer. Dashed black lines are moist adiabats, so it's about 6 Kelvin per kilometers. And these yellowish continuous lines that are tilted the other way, these are isotherms, okay? So I always get confused. There's a million lines in these, and so it's the easiest thing to get confused. Okay, so what we see here is, if we look towards the surface, here we have a layer from the surface all the way up to 700 millibar, and here from the surface to about 850 millibar. Notice that this is this temperature here is decreasing at a rate that is pretty much the dry adiabatic rate, okay? And so this is a classical example of what a mixed layer would look like. And because this is decreasing on a dry adiabat, you can almost be guaranteed that theta is constant over here, okay? And theta is constant over here. In both cases, these mixed layers are topped by some inversion. Here, the inversion is not so strong. Here is a lot stronger. And then the profiles decrease, but they don't decrease. The temperatures keep decreasing, but notice that it's not decreasing as dramatically as the dry adiabatic lapse rate, and this is due to the presence of the water vapor that mitigates the effects. And at some point between 175 and 150 hectopascals, then the temperatures start increasing again, and you know that here you've reached the tropopause, okay? So from here on, we have the stratosphere begins, and here it's slightly lower. But anyway, in terms of the mixed layers, they're pretty significant features here, okay? Okay, so when you do have the water vapor, then things are a little bit more complicated, and you can't just assume that theta is going to be constant. In general, theta will not be constant. But so instead of theta, we can define a new temperature. We're not going to go through the derivation of this because that would be needlessly cruel for this class. And I can just give you the formula here. This formula is the equivalent potential temperature, okay? And this is the temperature that a parcel would have if you were to condense all the water vapor in it and bring it adiabatically to the pressure P0, okay, to some reference pressure. Notice that this depends on the temperature of the lift and condensation level, which is what we sometimes call cloud base, and this temperature can be computed simply like this. This is the water vapor mixing ratio, and this is the latent heat of vaporization. It's about 2.56 times to the 6 joules per kilogram. Okay. This variable is more or less conserved under adiabatic motions and under phase transitions such as the condensation or evaporation of rain. Okay. Good. Yes. This is pretty much what I was just saying. Okay, good. So these are the basic equations that we need to characterize the motion of the atmosphere. As it turns out, these are still too complicated to put on a calculator, well, better, they're not too complicated to put on a calculator. There are ways to simplify these equations that can, A, facilitate the calculation on a computer, and B, give you a better insight as to what's going on, okay? So that when you look at a weather map, there are ways to massage these equations and introduce further approximations so that you can look at a weather map and you can learn something more about what's going to happen. On the other hand, if I just give you the Navier-Stokes equations plus some thermodynamics, it's almost impossible to figure out what's going to happen if I give you a weather map, okay? Okay, we will not get into those equations right now, those simplified equations, but instead we'll introduce one of the main characters of the remainder of the class. And this character is the geopotential, okay? The geopotential it sounds like a fancy word, but it's really nothing particularly fancy, nothing particularly complicated, and it's just something to get used to. The geopotential is a variable that is needed because the Earth is not a perfect sphere, okay? The Earth rotates, and because it was rotating when it was still in a quasi-fluid state, the Earth does not have a perfectly spherical shape. It would have it if, more or less, it would have it if it was not rotating, because gravity would pull every single grain of sand towards the center of the Earth with the same force. But unfortunately, or fortunately, I don't know, because the Earth is rotating, the gravitational force, the centrifugal force, which is also not a real force, but it's simply a consequence of the non-inertial frame of reference in which we're considering things. But anyway, the centrifugal force pushed the equator out a little bit, and so that the Earth looks more like, has a more oblate shape and not a spherical one. And therefore, instead of just considering the surface of the Earth, we define a field, okay? And this field is called geopotential. And this is defined such that the gradient of this field is exactly the gravitational acceleration. The gravitational acceleration is about 9.81 meters per second squared, but it's not the same at every point on Earth, right? If it was, then we wouldn't need the geopotential height. But the gravitational acceleration on the equator and on the pole is different. Not by a lot, but it's different enough that this difference should be taken into account. This also means, among other things, that you would weigh more or less depending on where you are. Okay, being in Hawaii and being in the North Pole is going to have a difference on how much you weigh on a scale. Okay. For convenience, we define the Earth's surface as the surface of zero geopotential. Okay. Another way, if we consider this equation, right, G is the gradient of phi, we can also integrate this in Z, and this tells you that the geopotential field is simply the integral of G in dz, okay? As we said, G is not a constant, so it's not a constant by latitude, and it's also not a constant by height. Remember from physics how you obtain G, right? You obtain G by writing the Newton's force of attraction between two astronomical bodies, like, right? So F equals G times big M times small m divided by r squared. So then you take G times M divided by r squared, and this is what you would call small g in this case, right? G, the big G is the gravitational constant, and this is the small case g, which is given by big G times big M divided by r squared, is the gravitational acceleration. Okay, so G is also a function of z and depends, and is inversely proportional to the distance from the center of the Earth. Okay, so it's a little bit more complicated, and that's why we cannot pull G out of this integral quite so simply. So the geopotential is measured in units of meter squared over second squared, and so these are weird units, and so we can take an average or an effective G0, and we can divide the geopotential by the G0, and this gives us a new field that we call geopotential height. Okay, so you could think of geopotential height as a better way to measure altitude that takes into account the oblate shape of the Earth's atmosphere. Okay, by and large, you can think of Z as the real altitude. Okay, the differences are not that significant that would give a completely different perception of reality, but they're significant enough that if you're trying to create accurate forecasts, you need to take these things into account. Okay. Okay, and so we like the geopotential and the geopotential height because it's going to introduce a couple of interesting points, and in particular, it will help us talk about the thermal wind and the jet streams, which we're going to talk about in a minute. First of all, the important thing that I want to point your attention to here is the bottom equation here, that if you do some massaging from the equation that I defined before, remember that the geostrophic wind was defined as the cross product between the unit vector pointing outward and the pressure gradients. But now there is a direct relationship between the geopotential and pressure variations, and so you can relate the geostrophic wind directly to the geopotential heights, or the geopotential, if you will. Okay, so whenever you encounter gradients of the geopotential, there you know that there is geostrophic wind that is traveling. Okay, and in particular, if you notice how this is defined, the geostrophic wind will always be perpendicular to gradients of the geopotential. Okay, we can do some more massaging of equations, and in particular, we can start from this equation that relates geopotential to pressure using alpha, and alpha is essentially the inverse of density, and we can use the ideal gas law. Okay, and so from the hydrostatic equation, you use the ideal gas law, and you obtain this very nice equation. Can integrate it very simply, and we obtain this simplified equation that relates changes in geopotential or geopotential height, whatever you prefer. The two, geopotential and geopotential heights, are simply related by a constant. Okay, so they're very similar. It's just a different units of measurement, also, and a slightly different magnitude. It's an order of magnitude difference because G0 is almost 10, right? And this relates the difference in geopotential height to, first of all, the logarithm between two different layers of the atmosphere, and the average virtual temperature of the layer between the two pressures, right? And so if we consider, for example, an upper level, if we consider a layer of the atmosphere that has an upper bound and a lower bound, then the difference in geopotential height between these two will be proportional to the logarithm of the ratio between these two, and it will be directly proportional, and this is really the key point here, it will be directly proportional to the average virtual temperature within that layer, okay? And so this is important because it tells us that pressure decreases more rapidly with height in colder rather than warmer air, okay? So consider the situation where we have, like here in the figure, right? This is a representation of a slice of the atmosphere. And at the bottom, we have the meridional coordinates. So these are latitudes, southern latitudes and northern latitudes. And the y-axis is height. Both start pretty much at the same level, so they're both at 1,000 hectopascals, 1,000 millibar. But in the tropics, the atmosphere is a lot warmer, and in the pole, the atmosphere is a lot colder. That means that layers of the atmosphere in the tropics are spaced out more than they are in the pole. And so if you are to connect surfaces with equal pressures, okay, so geopotential surfaces, these are tilted and they're slanted in different angles. And the higher you go, the more this gradient becomes. At some point, eventually, towards the top of the troposphere, observations suggest that the opposite happens. So the tropical atmosphere in the upper levels tends to be a bit colder than the polar atmosphere, and so this gradient relaxes, and then it reaches sort of an equal condition again at about 100 hectopascals. But so because of what we just said, that means that the gradients are maxima at some point in the middle, and this means that there's going to be pretty strong geostrophic wind over here in the middle, okay? Because the geostrophic wind is proportional to the gradient of the geopotential height on pressure surfaces, okay? Okay, and so, over here, the geostrophic wind increases. This is a maximum, and then it starts decreasing again. This is a prototype of what we would call the jet stream. So the presence of currents of air in the upper troposphere that travel at pretty fast speed, and these are due essentially to these tilting of the geopotential surfaces. This is a view of the atmosphere, and this in particular, it's showing 500 millibar geopotential heights, okay? And how close these are is again an indication of the presence of geostrophic wind for what we just said. And so notice how there's almost nothing next to the tropics in tropical regions. So in tropical regions, the geopotential height doesn't change much. And then the change happens pretty quickly in a fairly narrow band in the mid-latitudes, okay? At about, I would say, 30 degrees north. And so this is where one of the two jet streams can be found, okay? The subtropical jet stream can be found around here, and is due to the sudden change in geopotential heights. Okay, so the next thing I want to introduce that is a related concept to this is the thermal wind. Okay, so the geostrophic wind relation essentially is linking wind, geostrophic wind, with geopotential heights, okay? And there are many ways of writing this. We want to know how we can relate differences in geostrophic wind, otherwise known as wind shear. Well, wind shear is really differences in wind, and in this case, it will be geostrophic wind shear. Can we relate these to geopotential height gradients? Okay, and the answer is obviously yes, and this is what we know, what we call thermal wind. Okay, and we can look at this by defining a new coordinate system, and in particular, we call these natural coordinates, and these are coordinates that are oriented with respect to the geostrophic wind. Okay, so we have a vector called S that is a unit vector that is parallel to the geostrophic flow, and N is a vector that is perpendicular to the geostrophic flow, or perpendicular to the height, geopotential height contours. It's the same thing, okay? And this is a very nice and convenient coordinate system, and in this coordinate system, the geostrophic wind can be written in this way, right? And so we can define the geostrophic wind for the upper level, for the lower level. And if you do, then the difference between these two that we're going to call VT are proportional to ddn of the difference between the geopotential heights of these two values. If we use the hypsometric equation that we defined before, then this can be rewritten modulo some logarithm of PL over PU, modulo some constant. This can be written as being directly proportional to the gradient of the average virtual temperature in that particular layer of the atmosphere between L and U, gradient in the n direction, okay? So we now have a statement that relates gradients in temperature with gradients in wind, okay? Differences between upper level and lower level wind. This is what we would call the thermal wind. And the thermal wind isn't really a wind per se. The thermal wind is simply a difference in winds between different heights, if you will. And we are interested in the thermal wind because the thermal wind balance is actually a pretty good balance, and it's a pretty good approximation to think that the thermal wind balance holds. Okay, and knowing thermal wind is important because wind shear can have detrimental effects to, for example, tropical cyclones. It has certainly impacts on advection of cold or warm air, and it also impacts the life cycle of convective storms. There are many other ways of writing what I just said. The thermal wind that I showed a minute ago was written in terms of natural coordinates, so coordinates that were following the geopotential contours, but we can also write it in terms of Cartesian coordinates, and we would get something like this. So Vt is proportional to the cross product between the vertical velocity, the vertical vector, and the gradient of Tv, and we can also rewrite this. So Vt in this case would be between two different values, right? But you could also turn this into, you can make these layers infinitesimally close, and so this would give you then a vertical gradient. In this case, we're taking the derivative with respect to pressure, and this is the relation that we really care about. dV dP is proportional to the cross product with the gradient of d phi dP. Okay, so the gradient of the horizontal gradient of the vertical gradient of geopotential or geopotential height. Okay, and this is a better representation of the jet, right? Before we had those surfaces that were like slanted at an angle. In reality, the changes tend to happen primarily in a narrow band, as we said before, and so the jet is typically confined at a given latitude. Okay, so this is interesting because the thermal wind is also related to the thickness, right, between two layers of the atmosphere. And thickness is really, remember earlier we talked about ZU minus ZL. This is also known as thickness, right? Delta Z, okay, over here. So this helps us introduce the notions of cold advection and warm advection. And we want to talk about this using this particular example, okay? So this is a pretty crowded figure, and it contains three things. The first are the red contours, and these are 1,000 hectopascals geopotential heights, okay? So this is an idealization of a low pressure system. And remember, air moves counterclockwise around the low pressure system. And the dashed black line here, these are 500 hectopascals geopotential heights. Okay, so we're looking at the red line is the representation of what's happening at the surface, and the dashed black line, what's happening in the mid-troposphere. And let's assume, just for simplicity, that these are the wind is moving geostrophically, okay, along these two lines. So if we go to the point A over here, we have the wind is going down in that way, the wind of the surface, near the surface, is going this way, and the wind at 500 hectopascals is going that way. And so we can subtract these two, and we obtain, this is vectorial subtraction, hopefully you all remember how to do it, we obtain a vector that is going this way. And you could do it for every single point, and you obtain, if you just take the Z1000 minus Z500, you obtain these dashed green lines. So the dashed green lines represent the thickness of the atmosphere, okay, between, it's essentially, it's the 500 minus the 1000, okay? So it's the value in the black minus the value in red. So for example, let's go here, 5,280 meters at this point minus 180 meter is 5,100 meters, okay, and so forth. So this thermal wind represents, in a sense, wind that is moving along these lines of equal thickness, as if this was some kind of a geostrophic wind, if you will, as if this was the geostrophic wind of the thickness, in a sense, right? You can think about it that way. And this is telling us also something else, because here, if we go to the point A, the wind is moving, generally speaking, from the south to the north. And so it's likely that this is taking air that is pretty warm and taking it up north. And so this is causing some warm advection near the surface. And at 500 hectopascals, something similar is happening. So the air is coming from the south, it's going up north, and so this is also going to cause some warm advection. And so these two things taken together suggest that on average, on this layer between 1,000 and 500 hectopascals, there is generally warm advection, okay? And notice that as we go from 1,000 to 500 hectopascals, the winds, the direction of the wind changes, let me think about it, clockwise, right? So this is something, this phenomenon is called veering, okay? So we say that the wind veers when it changes clockwise with height. And veering is in general associated with warm advection on Earth, okay? Whenever you have winds veering, we have warm advection. The opposite, if the winds turn counterclockwise, this is called backing, okay? And backing is always associated with cold advection, okay? We're talking northern hemisphere here, okay? So I apologize to people in the southern hemisphere, but these conventions hold for the northern hemisphere. And it's a pretty safe bet that veering, warm advection, backing, cold advection. And here, this slide is saying exactly what I just said now. We can go to another example, okay? And this is some GFS analysis for January 2010, okay? And this is showing a couple of things. So, well, you can see the orange lines are continental lines. So you can see the US here, Canada, Cuba, and the Antilles and whatnot. Dashed red lines are surface level pressure. So it's not geopotential height, it's surface level pressure. And the red numbers here indicate the pressure values in hectopascals. So here it was 1,000 geopotential heights, 1,000 hectopascal geopotential heights, and so the values are something like 60 meters, 120 meters, and whatnot. Here it's surface level pressure, so it's 1,032 hectopascals, 1,020 hectopascals. And the blue lines show 500 hectopascals geopotential height, okay? And so here we can play this game, and I would invite you to go to just download any map right now and try and play this game at home. So you could go to an area over here, This is an area of high pressure, right? Area of high pressure, the wind moves clockwise. So the wind is coming down, for example, if we go here, the wind is coming down this way. And 500 at 500 hectopascals, the wind is going down that way. And so if we go from here, we move to 500 meters, the wind in this case is backing. So it's turning counterclockwise. It's backing, so this is associated with cold advection. On the other hand, the opposite is happening over here. So the wind is moving now, and the surface is moving here. It's almost perfectly zonal, right? It's going that way. And it's coming down this way still. And so the wind is now moving clockwise over here. And so here we're going to have warm advection. Okay. So this is a first, rule of thumb, if you will. Whenever you look at weather map, if you want to know if the air is going to get colder or warmer, you can start to look at these two variables. You can actually just look at whether the wind is veering or backing in that area, and this will tell you something about whether we're going to have cold advection or warm advection. I don't want to spend too much time on frictional veering. Just keep in mind that all of this is true because we're moving in the free troposphere. If we move closer to the surface, then things become a lot more complicated. Okay. And in that case, we also need to consider the possibility that there is veering or backing that has nothing to do with advection, but it's simply to do with friction, because friction disrupts the equilibrium between pressure gradients and Coriolis. Okay. But for the most part, we'll stay away from the surface in this class. Okay, next thing, I want to introduce another protagonist of this class, which is vorticity. Now, vorticity is not really used a lot, but vorticity is a fundamental concept in fluid dynamics, particularly when the fluids are on a rotating sphere, right? If the sphere is rotating, if the body is rotating, then rotations are an essential component of what you're doing, of the system that you're looking at. And so vorticity is the quantity that helps you better characterize what's happening. Now, if we lived in a two-dimensional world, then you would be crazy not to study fluid dynamics using entirely and only vorticity, because for whatever reason, a two-dimensional world loves vorticity. In 3 dimensions, vorticity is a lot more complicated, and things are not as pretty as they would be if we only had 2 dimensions, but it's still a pretty fundamental concept. I don't think I need to remind everybody how to define vorticity. This is a simple equation. So vorticity is a vector, obviously, and it's going to have 3 components. By and large, we'll be concerned with the vertical component of vorticity. Okay, so this includes the zonal gradient of the meridional wind and the meridional gradient of the zonal wind. These 2 kinds of horizontal vorticity are also important, but they'll play less of a role for us in synoptic meteorology. They do play a role in mesoscale meteorology, for example, but less important for us. And so typically we'll be restricting ourselves to the vertical vorticity, and we will call this, I believe this is zeta, the Greek letter zeta, and we'll distinguish between relative vorticity and absolute vorticity. And absolute vorticity also contains the Coriolis parameter, which is given by the sine of the latitude times twice the rotation of the Earth. Okay. And so the because W is a lot smaller than U and V, and because of how the world works, dw dx and dw dy are pretty small. And so what really matters, even when we consider horizontal vorticity are vertical gradients of U and V. Okay, so what we would call vertical wind shears. Okay. And what else? And du dx and dv dy are a lot more important than dw dx and dw dy. Okay, yeah. So where do we have vorticity? How can we get vorticity? Well, we get vorticity in a variety of contexts. First and foremost, yes, well, if you have a vortex. I mean, well, duh, right? I mean, the wind here is changing direction constantly, and so du dy and dv dx are changing constantly, and so w is always non-zero here. But the sort of the important point I wanted to make here is that we also have vorticity when we have wind shear, right? Because in this case, imagine that this is a horizontal jet, right? And this is direction U, and imagine this is X and this is Y, right? The vertical direction. Notice that U is different at different Y's. And so if you were to compute du dy is non-zero here. And so vorticity is non-zero. And vorticity actually changes sign whether you are south of the jet or north of the jet. Okay, so this is something that we need to keep in mind whenever we talk about vorticity. It's not just the obvious candidate, but it's also whenever you have wind shear. In this case, this is a classic example of where you might have vorticity. So here there's the wind and it's turning, right? So it's obvious that there's going to be some vorticity over here. Okay. Here I'm showing, this is a GFS analysis from January 2010. Okay, we've seen January 2010 already. And in the left plot, the shadings here represent absolute vorticity. So here we're considering planetary vorticity and we're considering relative vorticity. And there are actually a lot of vorticity centers, right? And you notice that vorticity is increasing quite substantially as you go north, as you go towards the pole. That is partially related to the presence of actual vorticity, but it's also related to the fact that planetary vorticity increases as you go towards the pole. So no wonder that vorticity is increasing. If you only consider relative vorticity, then you'd still see that there are centers of positive vorticity, but the story is a bit more complicated. There are also centers of negative vorticity and whatnot. Let's see. This is a GFS analysis for 2020. Notice how many, this is absolute vorticity, obviously, and obviously there's a lot of values, a lot of pretty strong values near the pole. And notice that here it's negative vorticity, so you might think, well, wait a minute, what is going on here? Well, look at this contour. This is the South Pole. So we're in the southern hemisphere. So vorticity is negative in the southern hemisphere. And notice that there are a lot of vorticity centers, particularly around, these areas where we have these troughs and these waves. And since I mentioned two-dimensional turbulence, we're obviously not in two dimensions, but you might or might not remember that in two-dimension, turbulence is very different from three dimensions, right? In three dimensions, there is an energy cascade that dissipates energy from the larger scales all the way down to the smaller scales, right? And so if you start with a turbulent structure, this turbulent structure will develop smaller and smaller eddies and will dissipate all the energy in the smaller eddies. In two dimensions, it's exactly the opposite. And so you'd go from this, there would be an energy buildup from the smaller scales to the larger scales. And so if you are purely in two dimensions, it's natural to develop these vorticity centers that act almost like, like Jupiter's eye almost. And I don't know, this kind of reminded me of what turbulence in 2D could be like, even though we're not in 2 dimensions and the world knows this very well. But it's not uncommon in 2D to find, a lot of vorticity centers that get bigger and stronger over time. Okay, so how does vorticity change over time? Well, this is the other equation that we need to keep in mind, and I think it's the last equation for this lecture. Well, kind of really. The last important equation that you need to remember from this lecture. So we've seen thermodynamic equations, so ideal gas law, momentum equation, continuity equation, first principle of thermodynamics, and now the vorticity equation. This tells us that the absolute vorticity changes in time either because of horizontal advection, vertical advection, tilting of horizontal vorticity into a vertical axis, vortex stretching, or differential frictional processes. Okay, we're not going to go through the derivation of this, so please trust me that this is what it is. Okay, and we could also do. Keep in mind that this is absolute vorticity, right? Not just relative vorticity. And we could look at some of the terms. For example, this is another GFS analysis from January 2010, which the author of the textbook apparently likes very much. And here we have two vorticity maxima over here. And the shaded areas here represent vorticity advection. So white is about 0, positive vorticity advection in orange colors, and blue colors represent negative vorticity advection. Notice that there's positive vorticity advection upstream and negative vorticity advection. There's positive vorticity advection downstream and negative vorticity advection upstream. Okay, so this is moving down, and so this is going to cause an increase of vorticity here and a decrease here, so that this eventually manages to move to this side. Okay. There's also a way to, if you massage terms a little bit, you could also rewrite the vortex stretching term. This one over here, you can also rewrite it. Sorry, I keep going back and forth. Remember that zeta A is the sum of zeta and F, okay? And remember that d omega dp can be related to the horizontal convergence by continuity equation. And so you obtain something that looks like this. Convergence of horizontal winds and relative vorticity and planetary vorticity. So this suggests to me that this term is pretty important when we have systems that have some cyclonic vorticity already going. Northern hemisphere, cyclonic vorticity, so F is positive, cyclonic vorticity is positive. If you have some convergence, then vortex stretching is going to lead to an increase of vorticity. So that's good. So if you have like fronts or troughs, vortex stretching can lead to an increase of vorticity. So it could lead to an intensification of, some extratropical cyclone or a cutoff low. If, on the other hand, you have areas of anticyclonic vorticity, then zeta and F have opposite signs, and so this term overall tends to be pretty small. And so vortex stretching is not important for anticyclonic vorticity. Okay. I wanted to introduce, sort of to conclude this lecture, I wanted to introduce a kind of motion that will play quite a role for us. And this motion, or this phenomenon is known as Rossby wave. And we look at Rossby wave considering a barotropic atmosphere. This is a very strong approximation, and it's not always true, but it's good to sort of understand the general behavior of the atmosphere, okay? And barotropic atmosphere means that density depends only on temperature, okay? And so if you remember the ideal gas law, this means that temperature is constant on isobaric surfaces, okay? You can work out the math and you'll see that geostrophic wind must be independent of height as well, okay? And the flow needs to be also non-divergent. If you work out all the math, then you'll see that the absolute vorticity needs to be conserved on the flow, okay, on a barotropic atmosphere, okay? And so this has an interesting consequence, because if let me go back once. Okay, so the sum of these two need to be conserved, okay? But that means that if you take a parcel of air, let's say that it doesn't have any vorticity to begin with, and you displace it, let's say northward or southward, then this parcel needs to develop some vorticity in order to maintain the absolute vorticity at zero, okay? So if you displace the parcel northward, F increases, and so zeta must decrease to compensate, and so you develop an anticyclonic turn. And so this, you start to go north, the anticyclonic turn will make you go south now, and when you overshoot the original point where you went, the opposite must happen. Now, F has decreased, and so you need to develop cyclonic motion. So you develop a cyclonic turn, and up and down, and you just keep going essentially, okay? And you develop what is known as a Rossby wave, okay? You can work out all the math. And if you do, you'd get to the equation of a wave that moves with a certain phase speed. And if we assume that this wave is moving with some kind of velocity u, and we assume that it has a nice sinusoidal profile that is moving with some phase speed c, then c is related to the speed of the background wind, but it's also related to the beta term, and it's also related to the length scale of the planet we are considering, okay? Rossby waves are a pretty common occurrence in the atmosphere, and they're pretty much everywhere. So here we're showing these time longitude plots. These are known as Hofmüller diagrams, and these are 500 hectopascals geopotential height anomalies. The left plot is from the month of November 1949, and it's encompassing the entire northern hemisphere latitude belt. And this one over here, the right-hand side, this is from April, May 2010, okay? Notice how you have this propagation of lows and highs and lows, okay, going down this way. So time is moving this way, right? So as time is moving, you have this propagation to the right. And it's to the right because, among other things, the velocity is winds are westerlies, right, in the mid-latitudes. And so the winds are propagating to the right. And this is another example of a Rossby wave propagating. And this is pretty ubiquitous in the mid-latitudes. Just wanted to say a couple of words about micrometeorology. I don't think we need to get into it. Just know that what we're going to talk about is mostly at the synoptic scale. But if we wanted to do things completely and carefully, then we would have to also consider what is happening in the boundary layer. Okay, the boundary layer is producing fluxes of things like temperature and water vapor and any kind of chemicals into the free troposphere. Okay, and it's also acting to produce friction, which will have an impact on certain systems as they move through the atmosphere. we will not have to worry about it, and so we can forget about micrometeorology, at least for now. Maybe we'll get back to this, but we don't have to worry about it too much. Okay, so this is pretty much what I had to say about these basic definitions. Any questions, as always, let me know, and we can talk about it in class as well. And I will see you next time for a very interesting lecture about the quasi-geostrophic approximation and quasi-geostrophic equations. Thank you.